This is the story of how we might discover life outside our solar system. Here is a star in our galaxy. It's a bit cooler than our Sun, which means it emits more red light and less blue light. It's also a little smaller, which means it emits less energy. This orange star therefore has habitable zone that's closer in than our own suns. By luck, a planet forms in that habitable zone, not too cold, not too hot. The planet is a terrestrial world, composed of rock and metals, though this time the entire planet is molten. It's large for a terrestrial world, heavier than our Earth, what we would call a super-Earth. Now, asteroids and comets bombard this super-Earth during its formation, sometimes really violently. The surface remains molten for many, many years. The planet's gravitational pull also captures a few asteroids, which become small moons. As the planet cools, its outer layer becomes solid. This is the first crust for our super-Earth. Beneath the crust is a thick liquid mantle with convection currents. These start the process of plate tectonics. The planet's crust will be moved and recycled over time. The water and gases delivered by all the bombarding comets contribute to the planet's atmosphere. The planet's high mass and resulting gravitational pull allows it to retain a fairly thick atmosphere. This will be essential in protecting its surface from heavy radiation from its star and will also help moderate the atmospheric temperature. As the planet cools even further, atmospheric water vapor becomes liquid and rains down onto the planet. Seas and lakes develop. Because the planet is in its star's habitable zone, most of that water will remain liquid, though the planet may develop ice caps, like our own or the ones on planet Mars. We now have a place of shelter, where many elements mix together in a warm churning sea. This is the sort of environment where life can develop. Rains bring nutrients from the land onto the sea, where they collect along the shoreline. These mixing chemicals, with some energy from heat, light and electrical discharges, combine to form amino acids, lipids, and other simple organic molecules. These in turn react with each other to produce longer and more complex molecules, similar to RNA. These molecules both store information and catalyze their own creation, making it easier to form more of this alien RNA. The process actually helps itself continue. Now, bubbles from the sea foam collect lipids, forming a simple surface, the first prototypes of cell membranes. As time goes on, these bubbles fill with water, salt, and nutrients, as well as some of this alien RNA. When these surfaces allow certain molecules to enter and others to leave, we have the first true cell. The alien RNA provides genetic information and replication. The nutrient-rich salt water provides the cytoplasm. The bubble of lipids provides the cell membrane. So cells require genetic material, cytoplasm, and a membrane, and this environment has created all three of them. At this point, evolution becomes possible. When the RNA replicates itself enough, it will split the bubble in two, and cell division begins. The alien RNA will be changed by radiation or replication errors and other factors. In each generation of change, the cells are challenged by their environment. So, cells with changes that don't help them survive and reproduce will be crowded out by the cells with changes that do help them survive and replicate. Cellular processes will become more complex and robust, and this evolving life will be able to survive beyond the place where it first arose. As the cells divide and reproduce, more and more of the planet becomes a home to life. And life, even single-celled life like this, produces byproducts. Modern plant life on Earth produces oxygen gas, but early life on Earth found oxygen poisonous. So we know that not all life needs or produces oxygen. Life on our hypothetical planet produces methane as a byproduct, as well as nitrous oxide. These chemicals will be our clue that life is present on this super Earth. Now, back on Earth, we're surveying the sky for new planets. At some time in our future, our telescopes happen to view this star. The star brightness and color tell us about its size and its mass. We see the star's brightness dim periodically, indicating that it may have a planet orbiting it with a transit we can detect. Continued observation confirms this cyclical light pattern, so we bring new instruments to focus on the star. Examining this light curve closely and using what we know about the star's own size, we can estimate the size of the planet. Now we bring a spectrometer to use, and it lets us see very precisely what colors of light are coming from the star. These colors oscillate as the star moves towards us and away from us due to the Doppler shift effect. Knowing how fast the star moves and how massive it is, we determine the mass of the planet, as well as the radius of the planet's orbit. From all this information, we on Earth find out that the planet is within its star's habitable zone and that it is a super Earth. Now we examine it more closely. Very careful work with the spectrometer will tell us what colors of light are coming from the planet and which wavelengths are blocked by its atmosphere. Most interesting to us are spectral lines that would indicate the presence of volatile gases like oxygen gas, nitrous oxide, or methane in the planet's atmosphere. The spectral lines from this planet show a great amount of methane gas, much more than could be explained by volcanoes or other non-life-based sources. As we watch carefully over the course of several years, we confirm the presence of methane, as well as nitrous oxide, another marker of biological life. The evidence is clear. We have found a planet with life. Well, this is only one way the story might come out. For now, we will need to keep watching, keep exploring. As new technologies and techniques improve our ability to view and measure the universe, it's only a matter of time.